Is this going to work now? I hope. Okay, so we'll say PCA. Okay, all right, principal component analysis. So the idea is you have high dimensional data. And we'll say this data is in m dimensions. And we want to reduce the number of dimensions down to d dimensions. But it's not really reduce. Reduce the number of dimensions okay. It's what it really is we are projecting down. Projecting down the dimensions. Okay, and we do this all the time. Okay, the book uses an example, which is when you see a shadow on the ground, you are seeing a two-dimensional projection of a three-dimensional object. Okay, and the truth is anything you see on a screen is a two-dimensional representation of a three-dimensional object, right? So so we experience this all the time in that, any image seen on a screen is a, three-dimensional object projected onto two dimensions. Okay, and so, you have so even when I try my terrible attempt at drawing a three-dimensional object here, okay, even this is a two-dimensional representation of some three-dimensional object, okay, and that's just the limitations of drawing on a two-dimensional surface, okay, and the idea is we want to do something similar with data, okay, maybe you've recorded 40 variables per observation, okay? And maybe that's just too many variables for you to fully appreciate and understand and visualize. And perhaps there's a way we can project that information down onto, two dimensions or three dimensions that still captures the essence of what this information represents. Okay, so perhaps we have 40 plus 40 dimensions, and that may be, quote, too many to understand well. Okay, I can't undo here. So we try to find a projection where a projection where kind of the, quote, essence of the data is retained. Okay, all right, I'll try forgive this example, but maybe, okay, so we can think of here, I'll give you like a political example, okay? So perhaps we ask a whole bunch of political, policy-based questions, right? So, we ask a bunch of people, policy-based questions. Okay, and so maybe you say, what's your opinion on gun control? Okay, and then we have, maybe these are all on scales, like from 1 to 5, and whatever 5 is like no gun, maybe 1 is like no gun control, and 5 is I'm all for whatever rules and stuff. And then you ask questions about how do you feel about abortion, and how do you feel about I don't know, welfare, or I don't know, all sorts of questions. What are other questions that Social Security, and what's that? Taxes and unions, and et cetera, et cetera, et cetera. Okay. I don't know, union/bargaining, collective bargaining, whatever you call these things, okay, et cetera, et cetera, okay. And this is just in the United States, right? Because these are like the topics that, or how do you feel about climate change, and pipelines, and all sorts of things, right? Okay. And and people, or and like should the government allow, I don't know, whatever. Okay, so there's all sorts of topics, right? And we can imagine like 40 questions, all right? And people can answer all of these things. I feel this way on this subject, and I feel this way on this subject, and I feel this way on this subject, right? And maybe we can look at all of this and we go, oh wow, there's a lot of information here, right? But chances are is that we can probably, okay, and this is not going to apply for everybody, all right? But by and large, if we looked at, let's just say we went to Congress, right? Okay, or maybe the average citizen is going to be different. But if we went to people in Congress themselves, okay, so you've got how many representatives? 435 representatives and 100 senators, right? So you got 535 members of Congress, and we survey them on all of these things, okay? Chances are is we could reduce all 40 of these questions or these dimensions, right? So we could imagine 40 plus questions or dimensions. This can probably, and this might be able to be reduced down to a single dimension, right? And what would that dimension be? Conservative liberal, or Democrat Republican, or something like that, right? So on one side we could put we'll put Republican on the right hand side, and we'll put Democrat on the left. Okay, that's just traditionally what we do. And then it's like, okay, somebody shows up over here. This means, they're going to feel this way about gun control, about abortion, about welfare, and probably, they'll feel, basically, if you say someone is over here on the Democrat-Republican spectrum, we can probably predict quite well how their opinions are on all of these subject matters, okay? And then if we say another congressional representative is over here on the scale, we can probably predict fairly well their opinions on almost all 40 subjects, right? Okay, and of course, some people, and then there might be some people kind of closer to the middle, like John McCain or something, who might stand out a little bit compared to their colleagues in Congress regarding their alignment. Okay, but if so, like like Nancy Pelosi would be like way over here, and we can or without even saying a name, if you say someone is over here, we can predict pretty well their opinions on a lot of these subjects, right? Someone over here. Predict a lot of opinions by knowing just this single aspect. Okay. And okay, and so this would be an extreme kind of like we could do principal component analysis and get it projected down onto a single dimension, such as this. Okay, or other places will try to expand this and have maybe two dimensions, and they'll have like social and a fiscal, and then you have basically more control socially and less control fiscally, aligns you a certain way. Less control social, less control fiscal aligns you another way. That would be like libertarian, and then more social and more fiscal influenced by the government would be make you a populist and things like that. And then you kind of have these other political dimensions, but this would also be another way of projecting 40 dimensions or whatever down onto just a couple dimensions. Okay, rather and then of course you're going to have some people that say, oh, you know what, I align very much this way, but on this one subject I'm different, right? And you say like I on all of these topics I align quite closely to this party, but then on these two subjects I feel very differently. Okay, that's going to be lost when you do principal component analysis. Okay, because principal component analysis is you're reducing all 40 dimensions down onto one or two dimensions, and so maybe if in all of these 40 questions there's like one or two things that stand out, that might get lost. Okay, and it's kind of, well, instead of having 40 pieces of information on every single person, we've reduced it just down to one or two pieces of information for simplicity. So yeah, we're going to lose some details that maybe make some people stand out. Okay, does that kind of make sense what we're doing as far as principal component analysis goes? Okay, and so when we do PCA, what we are often going for is you could have, let's say, here's data in 2 dimensions, okay? And you can think of, a projection as, you just shine a light and then see where the shadows are cast. Okay? If this is 2-dimensional data, we can shine it into just 1 dimension. All right? And then so if one, I put so imagine, okay, I should put the sunlight over here, but so imagine the light coming from this direction, okay? Then the data gets just projected down onto here, right? Okay, and then so this is one possible dimension. That's one projection. We could also just project it onto this axis. That's another way, or another way is I could project I could say the light's coming from over here, and then we would project it kind of onto here, and we would get the this would be another possible projection of the data onto here. Okay, probably a bad projection would be to put the light source over here. Okay, because if I did that, then almost everybody would look almost identical, right? Because the entire projection would just be in this tight little span here. Okay, so so probably the green projection is good, the red projection bad. Okay. Okay, and generally what we define as a good projection is the projection that maximizes the variance captured. And then when we do principal component analysis, if you have m dimensions and you're projecting them onto d dimensions, okay, or whatever else it is, okay, or another set of, or if you say d is equal to m, so basically you're setting another. Like if you have 10-dimensional data and you're going to do principal component analysis onto another 10 dimensions, what ends up happening is you're just providing what we call a rotation of the data. Okay, so so let's say we have m equal to 10 dimensions. Okay, so we perform PCA so that our 10-dimensional data is projected onto another set of 10 dimensions. Okay, and what happens is that the first dimension out of this new set of 10 dimensions, the first dimension is going to be the dimension that captures the most variance. Okay, the first dimension is the dimension that captures the most variance. And when I say dimension, this is just a linear combination of the other dimensions, okay? Okay. The second dimension is orthogonal to the first dimension, and captures the second greatest amount of variance, and so on and so forth. Okay, and then the third dimension is orthogonal to the first and the second, and then captures the third amount of variance all the way down to the 10th dimension. Okay, and the 10th dimension is orthogonal to the first 9. So all 10 dimensions will be orthogonal to each other. Okay, it's hard for us to visualize anything more than 3 dimensions that are orthogonal to each other because we only live in 3-dimensional space, and so we only can visualize 3 orthogonal dimensions. But in higher dimensional data, you can have more dimensions that are orthogonal to each other. And what principal component analysis does is it puts the each principal component is the new dimension that is orthogonal to the other ones. Okay. And so let me see if I can pull up my. No, that's not what I want. How do I get the apps? I forget how to use this computer. All apps. I want Firefox. Here we are. Nope, not this one. Okay. So here's oh, you guys can't see this now. Okay. Well. So this is I don't know if you guys can see this. Okay. So here is our original data. There's 5 data points in it's purple on my screen and I guess gray on the projection here. Okay. And we can see that if the principal component is going to be a projection of this data, okay, onto a single dimension, and this is the and it looks like this, okay. And so you know, if I suddenly turn this like this, okay, now the kind of the dimension that captures all of the most amount of variance is going to be is if we projected it vertically on this onto the direction of this red. I don't know if you guys can see that. Well, it looks great onto this axis right here. Okay, and I guess the thing it projects it here, and you can see in one. The principal component, this is what the 5 data points looks like right here, okay? And so these 2 dots are in the original data are different, but when projected onto the principal component look very similar, okay? I don't know if you guys can see that. All right, and if I just kind of manipulate this around, I'll post a link to this this website. It's called Explain Visually. They do some nice things here. Okay. And so here, you know, we've got our original 5 data points, and we're just projecting them down onto one of them. And then the second dimension is going to be orthogonal to the first. Okay. And because we have 2-dimensional data, once I create my first principal component, there's only one direction that's orthogonal to it, right? So it kind of forces it to this. So therefore, this principal component captures the most amount of variation, okay? And then the second one is going to be the dimension that's orthogonal to it, and now the amount of variation it captures doesn't matter. And so here, there's very little variation captured on the second principal component. Can you guys see that? Okay. Whereas if we just use the original dimensions x and y, okay, x displays this amount of variation. This is the direct projection down onto this side, and then y displays this amount of variation if we just project directly onto the y-axis there. Okay. Yeah. Question.
Is the projection also reorienting itself, or is it just generally in the middle on this?
It's every time I move this data around, it reorients the projection. Yeah, it's kind of a neat little.
Is the reorientation scheme important here?
Yeah, we'll talk about that. It's it the way it gets reoriented is based on the eigenvectors of the data here. Okay, but the idea is that this is what principal component analysis is doing. Right here, we've got some three-dimensional data. Okay, and this is what it looks like, and this is the original. These are three axes. I don't know if in red, blue, and green. These are your X, Y, and Z axes. Okay, and then I can hit Show Principal Component Analysis. Okay, and where do you think where the first principal component is going to align? It's going to align in this direction that maximizes the variation. We should see almost like three clusters appear in here. So if I click Show Principal Component Analysis, okay, it has reoriented the thing, and my computer's choking, but you can see this was the original data in X, Y, and Z, but after Principal Component Analysis, you can see kind of the three clusters appear just on the first principal component, okay? And then the other two, that variation is lost, okay, a little bit. And so what principal component analysis allows us to do is it allows us to do some effective dimension reduction, okay, while still managing to capture a lot of the key structure in the data, okay? So we're trying to capture the key structure without while reducing the amount of dimensions in the data that we have to do, okay? And then they do an example where, here's 17 dimensions on, the different kinds of foods that people eat in the United Kingdom, okay? They went to England and Ireland and Scotland and Wales. And again, here we have 17 different things, and it's hard to get an idea of, when you have this much information, it's hard to process this in our brain, okay? However, if we do principal component analysis, okay, and we project principal component analysis, what we see is that, okay, Wales, England, and Scotland, their dietary habits are more similar to each other, and North Ireland is quite different as far as dietary habits go, okay? Any idea as to why that might be the case? This is based on the data, okay? We asked people in the UK questions like how much we asked there are 17 things, how much alcohol do you drink, how much cereal do you how many cereals being grains do you eat, how much cheese, how much fish do you eat, how much fresh fruit, how many potatoes do you eat, how much vegetables do you eat, stuff like this, okay? And it turns out that when it comes to potatoes, North Ireland is potatoes and fresh fruit. Northern Ireland is quite different from the others. So if we look at these two things, this one here is fruit and this one's potatoes, and as far as England, Scotland, and Wales go, they all eat more fruits than potatoes, but in Ireland they eat more potatoes than fruit. And that is what captures as far as the amount of variation goes in the data, that aspect of variation is what separates kind of our groupings in the first principal component analysis, okay? And so that gets captured here, okay. So anyway, let's go back to our diagram. Okay, so principal component analysis. Let's see. Okay, running out of time. Okay. Well, I guess I can spend next lecture going over the math here. But do you guys remember eigenvalues and eigenvectors from linear algebra? Okay. All right. Okay. Well, if you've forgotten, it'll be good to review your notes for eigenvectors and eigenvalues. Okay. And eigenvalues. Okay, and I guess we'll discuss how eigenvectors, eigenvalues, and how the math plays into all of this for principal component analysis. But I guess today will just be kind of a conceptual display of how of what we're going to do with principal component analysis. There's a lot of neat applications for PCA. And then so we'll take a look at that on Wednesday, and then we'll play around with the math there. Okay, sorry about all the technical difficulties today. I hope maybe I'll try to find a cable that'll work next time. Okay. All right, let's see. How do I